Hello, this is a tutorial on how to do a two-way mixed ANOVA, that means analysis of variance, in SPSS. I'm going to start by talking through the example. This is very much for sports science, exercise physiology, sport nutrition. So if you are on that course and you're trying to learn about stats in that context, then this is the video for you. Our example data that we've got is looking at, does caffeine intake or caffeine supplementation influence someone's 5-kilometre running time performance? We're trying to also see if someone's training status influences that response to caffeine. So if we look at our data set that we have here, we have in the first column is everyone's who participated in the study's caffeine run time for the 5K in minutes. And we have the placebo run time in the second column, so when they just had a sugar pill and then did the 5K run. And then the third column, we've got the training status of each of our participants. So we compared trained versus untrained participants. And people with the number 1 next to their data points were untrained, and people that had the number 2 next to their values are trained. And this is really the crux of why we would use an ANOVA type of analysis, because we've got 2 different factors here. We've got our within subjects factor, which essentially means that all participants undertook all trials. So all 30 participants that we have here underwent the caffeine trial and the placebo trial. And then we have one between subjects factor, which was training status. So half the participants were classed as untrained and half the participants were classed as trained. So we've got a within subject factor as one independent variable and a between subject factor, training status, as our other independent variable. So this is the data view in SPSS. We'll go down to the variable view now and look at what we've got here. So what I've done is labelled the 2 within subjects factors in minutes, just so that will help my interpretability later. We also need to tell initially SPSS which values correspond to trained and untrained. So to do that, I'm going to go down to training status and then across to values, and I'm going to click on the cell, and then this little blue box is going to appear. So I'm going to click on those 3 dots, and then it's going to open this little window. So I'm just going to go and press the plus on the right hand side, and I'm going to type in value, and that's going to be associated with people who were untrained. So all participants in my data set that have a value of 1 in that training status column will mean that they are untrained. I'm going to do the same again and type in 2, and that corresponds with trained. And I'm going to hit OK then, and that's going to be all good there. I just want to double check that everything else is okay. So do I have the right number of decimal places for my data? Are the measure types appropriate? In this case, running time, 5-kilometre time trial performance. The unit of measurement is time in minutes, so that is scale data, so that's appropriate there. Separating groups of people based on training status would be a nominal category, so that's set as nominal. Okay, and then our data is pretty much good to go then. The next step we need to do is check the assumptions of the two-way mixed ANOVA. So we're going to start by looking at the normality assumption. So in other words, is the data normally distributed? And to do that, we're going to actually start by half doing the analysis and then generating something called the residuals. And they're what we need to check in an ANOVA. Are the residuals normally distributed? So don't worry too much about what the residuals mean or what they are. You can find plenty of things about that online. I'm not going to explain it in this tutorial, but I'm going to show you how to get them and how to test the normality of them. So we're going to go to this Analyze tab at the top, we're going to go to General Linear Model, and we're going to go to Repeated Measures. What you should do is have this first window pop up, and this is asking us to define our within subject factor name. So the way that we need to set it up is our within subject factor was condition, so caffeine versus placebo, so we're just going to name that the condition. You could call it supplement, you call it whatever you want. The main thing is you need to know what it is. And then it asks us for the number of levels in that independent variable. So in this case we've got caffeine and placebo, so that is 2 levels, so I'm going to type in number 2 and then hit add. That's all good then, so I am going to hit define. I'm then going to drag these 2 dependent variables, so the caffeine and placebo 5 kilometer runtime, onto the right box here. And then I'm going to drag training status down to our between subjects factors here. And then I'm going to hit options. And I'm going to check descriptive statistics, estimates of effect size, and homogeneity tests. I'm going to hit continue. We'll come back to that later, but it's just nice to do it now so that we don't forget about it. And then I'm going to come to save. And I'm going to check on the right hand side here something called studentized residuals. Then I'm going to hit continue, and then I'm going to hit OK. This is going to give us an output. So what I'm going to do is I'm going to close this output. I'm actually not interested in it yet because I still need to check that assumption of normality. So I'm going to close that off, not save it. And what you can see in my input window in the data view, I've now got these 2 columns. These are the residuals. And I need to do the normality checks on these. So to do that, I'm going to go to Analyze Descriptive Statistics, top here, and explore. I'm going to put my studentized residuals into the dependent list, and I'm going to come across to the right here and press statistics. That's fine. I'm going to come going to select plots, and then I'm going to uncheck histogram, and I'm going to recheck it again because we actually need that, and normality plots of tests, we're going to need that as well. So I'm going to hit continue, and now I'm going to hit OK. So what we have here is our descriptive statistics on the residuals, which we don't really care about. The first thing we're going to come down to is the tests of normality. So we're going to look on the right hand side here at the Shapiro-Wilk part, and we're going to look at the sig values. And an indication of normality with our data is if the sig values, also known as p-values, are above 0.05. In this case, they're both above 0.05, so it's our first indication that our data is normally distributed. But I want to stress here that this shouldn't be our only indication of normality. What we have is histograms, so looking at the pattern of this data, does it follow that typical bell-shaped curve? It does to some degree. It's not the most perfectly normally distributed data, but we'll take it. And then we can look at this thing called a Q to Q plot. So do these data points here in blue follow this line on the graph? If they do, then great, we've got a normally distributed data set. And what we can see is that it follows it reasonably well. It starts to go off a bit track here, and that would correspond with perhaps some of these residuals up here. I'm going to scroll down and look again at the other histogram. Okay, not as good as the first one, but still not completely horrendous. And same again with the Q to Q plot. They're reasonably close to that line. So I would be okay with assuming normality on this data set. One of the strengths of the two-way ANOVA is that it can be quite robust to deviations from normality. So in other words, if your data isn't quite normally distributed, it's still going to mean that the test results are valid if you use the two-way ANOVA. So that's cool. We've reasonably satisfied that assumption of normality. So I'm going to close that off now, and then I'm going to go back to that analysis process I was on a few minutes ago. So analyze, general linear model, repeated measures. SPSS is very clever, and it remembers the analysis that we set up previously, so we don't have to do it again. We can just carry on to define. And what we're going to want to go to now is plots. We're going to create a graph of our data, so we're going to drag training status onto the horizontal axes and have condition as the separate lines. Then we're going to hit add, and that's going to add this plot here, and we'll look at that in a minute. So we'll hit continue, and then we want to go to EM means, and what we're going to want to do is just drag this one called training status star condition across to display means for. What this thing is the interaction effect, and that's why we're doing a two-way ANOVA, is because the interaction effect tells us more about our data than if we used just a bunch of t-tests. So it'll basically say, is there an interaction between training status and the caffeine and placebo trials? So in other words, is caffeine's ergogenic effect, performance improving effect, influenced by what someone's training status is? If it is, it will show up in this interaction effect here. So I like to think of the interaction effect of the it depends factor. So looking at that's very important. So we're going to check compare simple main effects. And when we do that, it's going to look at the comparisons within all the groups. So it's going to compare caffeine and placebo in the untrained people. It's going to compare caffeine and placebo in the trained people. And it's going to compare caffeine in trained versus untrained. And then it's going to compare placebo in trained versus untrained. So quite a few different combinations of comparing our data. So because of that, we're going to change this confidence interval adjustment to Bonferroni. And this is essentially going to adjust our p-value. It's going to increase it because we're doing lots of comparisons. We don't want to accidentally find a significant result just because we've done lots of tests. So the Bonferroni adjustment will account for that. And you can look into more about how that does it mathematically. Again, that's beyond the scope of this video. But this is standard practice to include this Bonferroni. So that's all good then. We're ready to now hit OK. And it's going to give us our output now, so we're going to look at a few different things. So the first two boxes are quite informative because one, it will tell us about different variables and what numbers they're associated with, which is going to help for our interpretation, but it's also going to let us know if the number of data points matches up with what we're expecting. So in this case, condition 1 of our analysis is associated with the caffeine condition, and condition 2 is associated with the placebo condition. So it's good practice to write that down on a piece of paper and have that next to you because it will really help you interpreting the data lower down. Similarly, for training status, 1 is associated with untrained and 2 is associated with trained. This table here has our descriptive statistics, so the means for each group along with the totals for each trial. We're going to skip this box here and we're going to skip this box here. In fact, I'm going to delete them so that we don't have to have them in the way. We have this Morchley's test of sphericity then, which is another assumption check that we need to look at. with an ANOVA, but fortunately in our case, because it's only a 2x2 ANOVA, this doesn't apply in this case. This would only apply if our within subjects factor, so for example, in condition, so caffeine and placebo, if there was 3 levels there. So for example, if we did a study design where we looked at a placebo, then we looked at a low dose of caffeine versus a high dose of caffeine, we suddenly then would have 3 levels, and this would kick in then, and we would have to check that. But because we've only got 2 levels, this doesn't matter, so we're going to not worry about that and click delete. Okay. What we need to do is check our other assumption, which is the Levene's test, or equality of variances, and this is essentially saying, do the 2 groups that we have, the trained and untrained, roughly have a normal level of variance. So what we do is we read off this top row. So in the caffeine trial, there was an equality of variances. Our p-value was above 0.05, so that's fine. Then we look at the placebo, and we again look at the based on the mean, and that was 0.073, which is above 0.05. So we've met that assumption in that case, which is lovely. Now we can interpret the actual ANOVA, and this is the main table here, the test of within subjects effects. And if you come down to the middle, we've got this thing called condition star trainer status, and that's our interaction effect. And this is what we want to look at first in our ANOVA table once we've satisfied those assumptions. So we're going to read off this top row, sphericity assumed. So the reason we're doing that is because we don't need to worry about sphericity because we only had 2 levels in our within subjects factor. So sphericity can be assumed, and we can see that this sig value or p-value is less than 0.001, highly significant. And that's associated with a partially to squared of 0.597, which is also a large effect. Cool. We've got an interaction effect present. And you can verify that if you scroll all the way to the bottom and look at the graph that we made. An interaction effect is characterized by non-parallel lines. So you can see here our lines are non-parallel. So yeah, we've got an interaction effect. So now we want to probe that interaction effect, look at how things differ between training status and the condition. So we're going to go down to this first table that says pairwise comparisons. So what it's compared here is condition 1 versus condition 2. So caffeine versus placebo. What it's saying is, in the caffeine condition, untrained people had a significantly different 5k time to those in the trained group. So that's less than 0.05, so it's significant. Okay, and then in the placebo condition, again, untrained had a significantly different 5k run time to those that are trained. That comparison isn't really that informative or scientifically interesting, because we know that trained people are going to have a better 5k run time than untrained people, usually irrespective of what intervention that they receive. If we look at it the other way though, so going down to the next pairwise comparisons table, this is comparing, okay, if we look at trained people, how do they respond, or untrained people, how do they respond to the caffeine and placebo condition? And we can see that there's a significant difference there. So people in the untrained group had a significant change in their performance with the caffeine, whereas if we look at in the trained group, looking at caffeine and placebo, we can see that this is 0.0 or 0.780, which is above 0.05, so it's not significant. And this is where the interaction's coming in. So untrained people benefited from the caffeine intake, whereas trained people did not. And we can verify that by going all the way back to the top to our descriptive statistics, and we can see that the placebo, untrained, their time was about 33 minutes. When they took the caffeine, their time went down to about 31 minutes. So they had about a 2 and a bit minute improvement. Whereas in the trained group, with the placebo, it was 23.48 minutes. And with the caffeine, it was 23.4 minutes. So a very small difference that wasn't statistically significant. And that's what we'd want to report in our results. We want to essentially highlight this here, that in the untrained group, caffeine had an effect, whereas in the trained group, it didn't. And this could have some implications in terms of our interpretation of the results. Shows that if you say, oh, does caffeine improve your performance? You would say, oh, it depends if you're trained or untrained. If you're untrained, it will help you, and that might be because you've got more of a room to improve your performance acutely. Could be any other number of reasons, but there's just an example. And that's how we use the statistics, the two-way mixed ANOVA, and the interaction effect to give us a bit of depth and extract more information out of our analysis than just doing t-tests.